Okay, let's start. In last class, we talk about the minimum cover, right? The rules for the minimum cover. So we have a lot of definitions. So we talk about in order to be in, not this one. Where is it? Here. So in order to be in minimum cover, we have the following conditions. So 1, 2, 3, 1, emphasize on the right-hand side, 2, emphasize on the left-hand side, and 3, consider all the functional dependencies. And utilize this minimum set definition. Again, minimum cover, minimum set, they are the same thing. We can use this algorithm to find one minimum cover. Basically, step 2, 3, 4, they are following exactly same thing, which is in the definition 1, 2, 3 correspondingly. Okay, so let's see what we need to do here is let's first consider the logic here. We try to so for example, the set functional dependency input is E. And what we try to do is, firstly, I want to set my minimum cover F equal to E. So whatever the given input, I'm going to take all of them as minimum cover. And then using step 2, 3, 4, I do some transformation. Okay, I remove something, and eventually this E become something different. And in other words, originally the E is this big set, and then I remove things out, I modify the left-hand side, the right-hand side, and eventually this is my result. And that's the concept here. Now let's see how to do it. And first of all, let me talk about the rules here, like step 1, 2, 3, and 1, 2, 3, 4, and then I'm going to use an example to show how to do. Okay, so first of all, whatever input, I'm going to set my minimum cover equal to the input E there. And so we take everything. Okay, so now let's see, we first take them in, and then the second step, we want to check every single functional dependency. I want to see the right-hand side. Okay, so this is actually the simplest one. And so we check the right-hand side, and we can see if I have more than one attribute. In this case, we have A1, A2, AN. I need to break this into many different small functional dependencies. And the reason we can do that, because we have one inference rule called decomposition rule. We can decompose this big one into smaller one. And this decomposition results the same as the original one. Actually, I can show this to you. Inference rules. Okay, so that's actually this one. So if we have x to y, z, then we can do x to y and x to z. In this, using this decomposition rule, we can decompose the right-hand side into individual one, and we have multiple functional dependencies. Okay, so now let's see. We have this functional dependency replaced by that. And then for each functional dependency, x to a, this third step, this is the one we want to see the left-hand side. I think this is the hardest one. Okay, so let's see if we be able to understand this. Okay, so for each functional dependency, x to a here, and for this a component, I can have something, sorry, for the x component, we have something b here and something else here, right? So x can be more than one attribute. If x only have one attribute, then step 3, you don't need to do anything. Yeah, in other words, you can skip step 3 if there's only one attribute if there's only one attribute on the left-hand side, okay? And so now let's see for each attribute B, that's element of X, right? So element B is attribute. Element B is attribute in X, X is a set of attributes. And what we need to do is, I want to see if it is possible to remove B from X. So in other words, if we take this one out, right, and this is the only thing left, so what we have is not X to A, it's something else, right? Whatever left to A, become like that, right? So let's see, this is actually presented that. So first of all, X minus B, that means this part, right? Okay, and to A, and that's to A, that's what I have here. And let's see, X to A, that's the original one. F is what you get from step number 2. I always use previous step result and always follow this order. Okay, so step number 2, it told me I have X to A, I'm going to remove this. So F minus this, F is a set of functional dependencies. Remove this one, so that means I'm going to get rid of this. And then I'm going to union, means we'll add something in the set of functional dependency. That is this part to A. Okay, and so we want to see this kind of operation is equivalent to F or not. F is what you produce from the previous step, right? So if it's equivalent, that means what? I don't even need B. B can be removed. Means this original functional dependency, X has something unnecessary on the left-hand side. So this means I can remove B. Okay, so if this is the case, I'm going to replace X to A with X minus B to A. So if this is operations equivalent, I'm not going to see this anymore, right? So this is gone. And what I have is this part to A. That's what I have. So this is simply require that anything in the minimum cover, the left-hand side should only include the necessary information, not, arbitrary all the attributes, many attributes, just whatever on the left must be necessary for this functional dependency. And I'm going to show you an example on this. And then let's see step number 4. This one talk about after step 2's transformation, step 3, right? Work on number 2, work on top of number 2, and the 3 produce a result and pass the result to number 4. And at this point, we'll have different type of functional dependency from the original one, right? Because you see the transformation we have done. And from this one produced in step number 3, I want to see, do I need all the functional dependency? So for example, this is X-way in this result, and I found out I don't need this, right? I don't need, I found out I don't need this anymore, so I can go ahead to remove that. So that's why it tried to see if I remove something like this, whatever left is still equivalent to the original one. Means, did you, this kind of remove operation, is this kind of operation lose any semantic? And if by any chance we remove this, right, and whatever left is still equivalent to the original one, that means we don't need this. In other words, using the existing one, whatever left, right, we can infer this using inference rules. So that's why we don't need it. And so if that's the case, let's go ahead and remove it. Okay. So we have this, and let me give you an example. So to help you understand the minimum cover. Okay. So my example basically show different step, 2, 3, 4, what you need to do. And so let's see. My given, oh, I use different color. So the given set of functional dependency E, I have the following functional dependencies. Okay, and let me see, actually I can put on here so I can work on this directly. And then I have x to y, y to z, and x to z here. So that's all the functional dependency I have. Okay. So that's the input. Okay. So what we need to do, step 1 here, we want to set our f is the minimum cover eventually. And I want to set f equal to e firstly. So this is step number 1 here. So whatever in the given set of functional dependency, I will put all of them into my minimum cover here. Okay, so now let's move on to step number 2. And step number 2, want to check the right-hand set, right? So the right-hand set, if the right-hand set already have one single attribute, we do not need to do anything. But if the right-hand set has 2 or more, we need to break them into multiple functional dependency. So we can see this one, this one, this one, this one, all single attribute on the right-hand set. Then the only thing we need to worry about is the first one. So for step number 2, first of all, I'm going to replace this one into 2 functional dependencies. First functional dependency I have is SSN to ename. The second functional dependency I have is SSN to bdate. So that's what we need to have for replacement of second step, right? So you see this, we have this one, right? Okay, so I have that. And now let's see, since the rest of them only have one attribute, I'm going to copy this one here. Since I need to pass the result to the next step, right? So let me just copy it down so I can easily pass to the next step. Right, so this is the result of step number 2. And for step number 3, we are going to use the result of step number 2. So now let's see, what should we do for step number 3? That is, we want to check left-hand set. If the left-hand set has only one attribute, then we don't need to do anything in step number 3. But if we have more than one, then we need to do something. And we can see this is the only one has 2 attributes, right? So this one has 2 attributes on the left. So what we need to do is we need to go back to see this, right? So we want to see if something in the left can be removed, right? I don't know if this one can be removed or not, but we can try, right? So for this case, 2 things can happen. One is we can remove SSN. Okay, so let me put this one, maybe another color. So for this particular one, right? So possibly I put a question mark here because I only have 2 attributes. So possibly remove SSN from the left. Then I have DNO to ename. Okay. On the other hand, if I remove DNO, then I'm going to have SSN to ename. So they are possible way to remove. Also, it is possible nothing can be removed. Okay, we don't know. Not always the left-hand side must be one attribute. Sometimes it is okay to have two or more. Right? Not necessarily always one. So this attempt may not be successful. Right? So possibly three possible results in my step number 3 for this particular functional dependency. One is as it is, okay, no change. Another one is like this, another one like this. So how do we know which one is possible, the result? So in other words, can I use this to replace this? Can I use to replace that? And in order to know this, two things you can use. The first thing is whatever fact. Right? So given, and this can be the things coming from here, right? Like whatever listed here, or it can be coming from the original one, because this is actually using inference rule. This is equivalent to that. So you can use anything given, this is the original, whatever facts given here. And we are also using the one we produced. So that's the first thing we can use. The second thing we can use is we can use inference rules. Okay, so inference rules help us to know, is this the one can be used to replace that, or this one can be replaced that? And in this particular example, this is actually quite straightforward because we can clearly see I have an inference, I don't need to use inference rules because I have this functional dependency here, exactly same as this one. So in other words, if we check this one and this one, we can see we don't even need this DNO here, right? So we know ename depend on SSN already. And this one tell me SSN combined with the number determines ename. I don't need the number. SSN is self-sufficient to determine ename. The reason I know this because the first one tell me, and that's actually coming from the transformation of this one, right? So since that's the case, that means this attempt is successful. So in other words, I can remove DNO from the left-hand side and use SSN to ename to replace that. Okay, so let me write this down. So what I can do is I can use SSN to ename to replace. Right? Okay, so let me clean up to see what I can get, right? So I use this to replace that. This one, this one, this one, this one, this one. I need to copy it down. So let me put this one. Okay, and I have SSN. Okay, so remember this one is not there anymore. We use this to replace. So let me put this down. Okay, so this is the result number 3, but immediately we can see this and this, they are exactly the same, right? So they are duplicate. And then we want to see duplicate in the set so we can remove them. It doesn't matter which one you remove because they are exactly the same, right? Say I remove this one. So eventually I have 1, 2, 3, 4, 5 functional dependency that's produced by number 3. Okay, so number 4, okay, let's quickly go back. So number 4, this is the one we want to see all the functional dependency remaining produced by number 3. do we need all of them? Can we remove something, right? So let's see, when we take a look about the 5 of them, can we remove something? Oh, you probably already discovered this. Okay, so let me write this one somewhere, maybe, I don't know, which one should I remove? Actually, I don't need any of them. Let me clean them so to see things better. Okay, so what I have here is if I write this down like this, okay, so I can see using the inference rules, I can get this one, right? So this is one of the inference rules we learned. It's actually the same thing. This one. So I actually using the same symbol X, Y, Y, Z, right? So you have this one, right? Okay, so we have that. Okay, too far. All right, and so I know this is true. So this one tell you what? Once I know this, I don't even need this, but I can produce, I can use inference rules to deduce this one, right? So I know this is true just because this is true. So this is not necessary. So when we consider this one produced by step number 3, I can see, okay, oh, I removed that. Okay, so for the things I have here, I don't need this. So if I remove this, I have 4 left, whatever left, still equivalent to this one. So that's why, so this is the one. Okay, so if we remove this one, if we get rid of this one, 1, 2, 3, 4 equivalent to the 5. Okay, so that's why we can remove that. So as a result, we have the step number 4. Okay, we're going to remove X to Z, right? So my final result, what is the final result? That's, so this is my minimum cover F. And this one has SSN to E name, SSN to P date, okay, and X to Y and Y to Z. Okay. Okay. So you may ask, can I remove X to Y, but keep X to Z? The answer is no, because from Y to Z, X to Z, you are not be able to know X determine Y, right? Same thing for Y to Z. So only this is the one can be produced by X to Y and Y to Z. So that's why that's the one can be removed. Okay, so this one actually is a simple example. For example, for step number 3, the reason we can use this is just because we can directly see the functional dependency within the result, right? The previous result. But sometimes we can, more complicated ones can be the one you need to use inference rule to tell whether an element can be removed or not. And remember that okay, so this is the one tell you the right-hand set must be single attribute, but left-hand set, actually probably better take a look about this one. So this one tell you in order to be a minimum cover, single attribute for the right-hand set, but for the left-hand set, we don't require a single attribute. Eventually, you will have the functional dependency, possibly have functional dependency has 2 or more attributes on the left. Doesn't necessarily always can be single. Okay, Okay, so that's for minimum cover. And so now we finish the like the foundation part, functional dependency, closure, minimum cover. And now we finally dig into the main business that's called the normalization. So we prepare everything we had just for the normalization part. So what is normalization, right? So we heard about this at the beginning when we talk about this chapter. Normalization is the process of decompose unsatisfied relation. Usually they are like big relations, and we can break them up into smaller relations. Right? So maybe like somebody design something, one table contain all those attributes, and you're going to normalize them into smaller relations. And how do we do that? We are going to use keys, okay, and the functional dependencies. We just finished that, right? And the keys will do something very soon. And then using that, this is a basic normalization, and we want to eventually achieve the result that this design, right, the result is in particular normal form. In particular normal form, we actually will learn first normal form, second normal form, third normal form, and the both called normal form. Okay, so consider this, I start with number one, right? And end up with BCNF. And this is more strict than that. This is more strict than that. And this is more strict than that. And the BCNF considered as higher enough normal forms for practical relational design. Okay, so there are higher normal form that usually we don't necessary to dig into, consider the balancing of, for example, performance and everything. So usually when we design into third or BCNF, that's considered good enough. So you may ask, why not always BCNF, right? So why sometimes you see third normal form is good enough? It's just because actually we'll do that in 174. We have existing algorithm can decompose into third normal form with different properties. We have 3 properties. All of them can be satisfied if we decompose in third normal form. But if we decompose into BCNF, we are not guaranteed to satisfy all 3. So that's why sometimes third is also accepted. And for the scope of this course, you don't need to know that much. You need to know the definition of each of them. And you also need to know when I give you a question, you need to tell me, oh, this design is in, for example, third normal form. And we'll go over each of them, and I will have example for you. And I also will have in-class exercise. They are very important. And they are very important to prepare for your exams. Okay, so just treat in-class exercise the same way as you assignments. Okay, so let's see normalization. So practical use of this, let me briefly talk about this. And so the purpose of normalization is I want to have high quality design, right? So like I want to produce something in like third normal form. And the practical use of the normal form, some people criticize it because when we have normal form, we have to rely on functional dependency. And sometimes those functional dependencies are hard to understand or detect. So if we have problem with that, then our normal form can have issues, like when we use them for normalization. But on the other hand, the same thing, if you misunderstand user requirements, you produce a wrong ER diagram and you follow the mapping rules, or even you design correctly in ER, you follow wrong, you didn't follow the rules for mapping correctly, you also will have a wrong design eventually. Right, but that's some criticize on this. And also, this is what I already mentioned. You don't need to always normalize to highest possible one. An opposite process of normalization is denormalization. This is the one to combine small relations into bigger ones. So we can join some higher normal form relation into a bigger base relation. And they lower normal form. And usually we do that for performance purpose, for specific application, if certain things are more important, like performance. And we're frequently using two tables, and we may do denormalization. So this is outside of the scope of 134. This one you need to know, and you don't need to know that, and you need to know that. Okay. All right. Okay, so now still we need to review the things related to key. Okay, hopefully you still remember something. So first of all, if we think about super key, right? So we talked about super key already. So a super key relation is a set of attribute. So this super key must be set of relation R, right? So because we pick super key from A1 to AN, some attributes together as super key. Okay, we have the condition in order to be super key, then okay, if we pick any two tuple, right? And in any legal relation state, then we know the super key value must be, if, okay, so there's no tuple, okay? So you say T1, T2, you pick any two, there's no tuple, the super key value is the same. So in other words, if they are same, they're actually the same tuple, if we talk about set, right? And this is actually similar to what we defined in, in functional dependency, right? So it means everything else, okay, everything else is functionally dependent on the super key, okay? So if we take a look about functional dependency definition, any two, if we have the same X, right? You're going to have the same Y, then I have functional dependency X to Y. So in this case, no tuple should have the same value. That means whenever you have the same, they must be the same. In other words, they will be the identical one. Okay. And so as a result, when we calculate the closure, okay, maybe I should be using the same notation. So let me using this. So we're using this way, right? So when we calculate the closure, and that's attribute closure, and that is the one we did in here, right? So this is the way to calculate attribute closure. Attribute closure means the set of attributes that are functionally determined by X based on F, right? Okay, go further. Okay, so when we calculate the closure, remember everything else depended on, this is the super key, right? So everything else depends on super key. So if super key called K here, it can be a set of attributes. Then the closure of this will include all attributes. Because everything, so K itself depends on K, right? Everything else also depends on that. So that's why the closure of super key should including all the attributes. So this can be a way to decide whether something is a super key or not. Just using the closure definition. Okay, you don't have to use this, but this is just like one way. If you calculate the closure, get everything, you know that is a super key. Okay, so K is a super key. Key here, K is a super key with additional property, and that means remove any attribute from it, or of course it's not a super key anymore. This is the exact same thing we define for key. Key must be minimal, right? All right, so we know key must be a minimum super key. And if a relation schema has more than one key, so can have a couple of them, each of them is called a candidate key, right? So it's a candidate to be selected as a primary key. So if we have key 1, 2, 3, and we pick this one, that's the primary key. And the rest of them is called the secondary key. So this is secondary key. This is also secondary keys. Okay. All right, so now we are ready to talk about first normal form. The very first normal form we covered actually is already embedded into relational model definition. In a relational model, we do not allow composite or multi-value attribute. So you may say, oh, we did learn this, right? So we didn't learn, we did see this and this, but they are in ER diagram, right? So if we go back to mapping from ER to relational model, you will see we have a certain way to handle composite. We have a certain way to handle multi-value. In other words, we don't see them directly in relational design. It's just because in relational model, we do not allow those things in the relationship directly. Okay, so in other words, everything, like you have a table, right? So you think about table, we can have many components here. So any part you pick, it doesn't matter where you pick, this must be atomic value, okay? Means we cannot divide it, we cannot do a set, so this is not okay, right? So we cannot compose them, we cannot get a list of value or a set of values. This is not okay. So that's for this. And remember, whether it's divisible or not, this is on specific application. So in one application, you may think a name is not divisible, but in another application, maybe you feel name is divisible, can be first name, last name. So all depend on the application. Okay, so let's see something so actually, before I do that, let me show you one notation here. So remember, we have notation like SSN to e-name and address, right? Something like that. Okay, so let me show you another notation for this. So I can write down the attribute here, SSN e-name and address. And this notation, the only difference, there are different notations, and some people like this, some people like that. We are going to use this one in the rest of the normal form, so you better know this also. So what I have is I can do SSN to e-name. So and also I do address here. So this, anything without arrow means that's on the left-hand side, right? So you see this on the left-hand side. And everything on the right-hand side, they have an arrow point too. So this is equivalent to this, just different notations. They mean the same thing. They have the same semantic. Okay, so now let's see the first hold on. Click something. Okay, so now let's see the first normal form here. We can see in this example, we have department and department number determines the name and the manager SSN. So in other words, if you give the same department name, guaranteed to have exactly same department name and the same manager SSN. So name and the manager SSN is dependent on the number. So that's basically this part of notation I just show you, right? And this part is not any functional dependency notation, this is pretty much show we have a problem here, right? So we have a problem here. This is not a functional dependency. The reason for that is if we take a look about the instance, we'll understand. So when we have the same department number, I guarantee have the same department name and manager SSN. But this one, I have 3 locations. So this is not purely depend on department number. So this is the case that I have, this is the case of multi-value, right? So this is the multi-value attribute location. We have many of them. And if you remember what we did in the ER diagram mapping to relational model, we have the D location like this, but we map to table. We don't have things like this, right? We end with break into 2 tables. This is not this particular one, the one I show you here. This is not in first normal form, right? Since this is not in the first normal form, we cannot implement this directly in relational model. And you may argue with me, see, I can do this. I can put the whole thing as a string, and I just use a code to put things in, right? So yes, then in that case, you consider the whole component is one field, is one element. Where did I put this? So you have a table, right? So have a table, how many things, anything in the table here, you take the whole thing as a component here, and you think this whole thing is not divisible. So that's actually not the case, because if you want to retrieve, for example, Houston, then you have to take this one and to do some parsing in order to produce Houston only. Okay. And we finished SQL already, and you know how easy it is if you make an attribute equal to something. And if you design like this, for any query related to the location, you need to do some parsing here, because you don't know how many attributes possibly. In the result can be like a 5 location, can be 1 location, can be like 10 locations. Okay, so that's a lot of work there. So since this is not in first normal form, and then let's decompose this into first normal form. Okay, so let's see the solution here. The first solution is the best. And some of you probably recognize this is our solution, right? So that when we do the mapping, remember, and this is actually the way to do mapping. And we produce 2 tables, and we use D number as the primary key, combine like a number and location combines the primary key, and D number is a foreign key reference to this D number. Okay, and the second solution is I can combine D number with D location. We have some disadvantage of using this approach. Okay, so first of all, this approach is in first normal form. This is normalized into first. So this is the first, and also first. So in this case, I can say D name is dependent on the combination of number and location, and manager access also dependent on the combination. So let's satisfy the first normal form. However, when we have this D number, name, and manager SSN need to repeat it many times when we have many locations. So for example, I give you this example, D number 1 and location in A, right? And D name is CSC, manager SSN, whatever. And so that's fine if you only have like 1 location. And so number 2, department number 2, and location has in A, and like EE here, I will have number. And then for the same department number 2, I have another location, so I need to repeat this. And department number 2 has another location, I have to repeat this. So if a department has many locations here, then this field, number field, and this name and the manager access need to keep repeating. right? So you can do like waste your storage on something already there, but this approach, you're not going to repeat the name and the manager SSN. Of course, you have to repeat a number in order to be unique identified combined with the delocation. So this may not be a big deal since I only have 4 attributes. But if I have a lot of attributes and some of them, they are long strings, and then you actually waste a lot of space here, right? Okay, so that's for this solution. And then for solution 3, this is the one that I can have a department with the number unique and name. So this part is fine. But since I say I know I only can have maximum 3 locations, then I can do 1, 2, 3 here. Okay, so seems like a nice solution, but this one also have issues, right? So for example, if I have a new department added to the system, and that department has 5 locations, you have to change your schema. And remember that we try not to change the schema often, right? So we can, add a tuples, remove tuples, but we don't try not to change the schema often. So that's one disadvantage. Another disadvantage is when you do query, right? So you need to see all of them because there's no guarantee unless you write a certain program to, to have certain training on whoever inputted data. If there's only one location, you cannot guarantee they just put in location 1. So you actually have to compare, like maybe, this is null, and this is the location, and this is null also. So you need to check all of them and to compare. It just makes the query complicated, that's all. Okay, so that's all for this. I will talk more next class.